Welcome everyone to CSAI Week 4. Thanks for coming out and bearing the weather. I know it's a lot and windy, and thank you to the folks on Zoom for still coming in, even though you're not in person. I hope your bed is more comfy than the room. I am Leo, this is Amir, and we are going to hopefully present a topic today that is kind of a new sector of this vast world of artificial intelligence, and will hopefully kick us off into a new project launch that's coming in the next week or two that has to do with Wordle. So stay tuned with that, and we'll kind of lead into that. Anything you want to say before we get started?
Not much. I just think this is a really cool one.
I agree. Awesome. So what we're going to start with is called reinforcement learning. So to kind of put this into context, a lot of us think of artificial intelligence as maybe typical machine learning problems where you have like a cucumber and a tomato and you take photos of them and you want to classify them, right? Or maybe you want to be able to predict some patterns or find some patterns in data. Those are examples. Well, the first one, classification, is an example of supervised learning because you have the answer that you want, you have the labels to the data, and you want to classify it. The second is an example of unsupervised learning. If you have a bunch of people and you're trying to sell things to them and you want to group them into like interest groups, that's unsupervised learning because you want to have the machine figure out groups of those people to create. Where reinforcement learning fits in is instead of either of those, you have this thing called an environment or a situation where basically you have a computer, or in this case, what's referred to as an agent, which is a computer, take an action in that environment or in that situation, and you say whether or not that's good or bad, right? So do something and decide if it's good or bad. So you can imagine when would this be useful, right? So if we have like photos of tomatoes and cucumbers, that's very clear, supervised learning, they have the labels. What's a situation where we don't have the answers already and we can't train a model with the correct answers? What would be a situation where we would want to have an agent explore and then say whether the action that it took is good or bad? Does anybody have any thoughts? I can kick us off with one if we don't. Self-driving car. Like, you cannot imagine every possible scenario or every possible situation that a car could be in, but if it runs through a red light, you can say that's bad. And if it drives straight on the road when there's a double yellow line, you can say that that's good. Any other thoughts? Any other ideas? Yeah, James?
Then I'd say something similar would be like a robot.
A robot?
Trying to get it to walk, like falling would be that.
Yeah, that's a really good example. So on Zoom, the suggestion was a robot trying to get it to walk. So you don't really know how to program a robot to walk, but if it makes progress, you can say that that's good. That's a great example. Another example is games. So that is a hint, hint, wink, wink to the project later. But if you have like chess is a great example, and Go, right? Like all these AlphaGo models and all these things learning to play games. We can't even as humans think of all the possible combinations of all the games, but if you have a computer win at chess against a human, whatever actions it took were good, right? So, and then the last example we had was actually throwback to last week, if you were here or attended. Kevin from Meta talked about training training large language models using reinforcement learning. And I'll let you kind of take a look at the recording if you want more info on that, but really cool to see that they're using that along with large language model generation at big companies. So I want to make sure that we have this idea of an environment kind of well defined, or excuse me, that we're aware of this idea of an environment. So we're going to use this term a lot, and with all that it means is kind of a situation or a scenario where you can tell what's going on and you can tell what actions are good and bad. So when someone takes an action or a computer takes an action, you know what that action does and you know if it's good or bad. Because if you don't know what the action is, it's kind of unsupervised and you're kind of just saying, figure it out. But if you know, like in a car, if you know that it takes a left at a red light, that's bad, right? So does that
You
kind of,
don't actually have to know what the action does.
you don't have to know what the action does.
No, all that matters is that it affects the environment in some way, and the environment will give some feedback to the agent. For example, like I don't know, if you were some omniscient god looking into this room,
Yeah.
you don't have to know what John's gonna like say. It's because like if John like I don't know, does something bad or something in this room, you don't have to know exactly necessarily what's gonna happen in order for it to affect the environment in a negative way or a positive way.
Gotcha. So
The environment itself will give the reward.
right, okay, so the agent doesn't have to know what's gonna happen. But the environment itself needs to know how to react. So if you're like, for
Yeah,
example, if we're coding the environment,
Yeah,
that needs to know how to react if an agent takes an action.
the goal of the agent is to learn that kind of
Right.
thing. For
Right.
example, if an agent was playing Flappy Bird, it doesn't want to go into the pipes, so it has to learn that. And it will get rewarded negatively
Right.
if it hits the pipes.
Okay,
It's the environment that is the source of that signal. And the agent is simply interacting with that.
yeah, John,
You gave us like two snapshots of the environment. And you were in a state before, and you can quantify the reward for that,
yeah,
the reward for that. And then if your next state has less potential, you could say. And it has like a lower potential for a reward, then your action was bad. But you don't necessarily need to know how you got from state 1 to state 2 or ST to ST plus 1 in this case.
okay, gotcha.
Uh,
You can compare the two states to each other.
Yeah, you just take the delta between. the two.
Gotcha. Cool, so let's, before we jump into specifics and notation, I want to kind of give an overview of a more explicit definition of an environment, which is used in the context of the Markov decision process. And what that basically means is it's a chain of environments, one to the other. Like John was saying, we go from one state to another state over and over again, using the agent to make the decision. So anyway, this will become clear in a second, but can I ask the audience, if you're in a situation and you want to make progress, what things do you need to know? What do you need to know about the situation? What do you need to know about your actions? What do you need to know?
know what progress actually means.
You need to know what progress actually means. Yeah, so what does the next thing look like? And then by extension, you need to know what's good progress and what's not what's like regress, essentially. Yeah, anything else we should know? Yeah, the actions you can take, that's really good. Yeah, because without that, you don't know what to do. Okay, so we've got the actions you can take and when the state changes. Just to start off a more basic situation, we actually need to know the current state. We need to know what the situation is right now. Kind of to Julian's point, if it changes, we need to know what that is. And by extension, the current space, we can refer to that as what's called an observation. So we can observe the current space. And then
there's a difference between state space and observation space. Observation space is like what the machine can see, whereas the state space, it might be the same as the observation space, but the state space is like the whole state. So observation space at time step t in the Mario game would be the actual screen,
okay,
whereas the state space is like the state of the entire level.
gotcha. So like James was saying, the action space, the things you can take, and then there are a couple more here. The probabilities and the notation is a little bit complicated, and let me know if I'm explaining this right. The probabilities are essentially, if you take an action, you need to know, or the environment needs to know what probability that action has to lead to a different state. So as a simpler example, if you are tired and your options are to sleep, to go to the gym, to eat food, like what are the chances of you sleeping is going to make you not tired? What are the chances of you eating are making you not tired? Obviously, the chances of you sleeping is probably a little bit more. Yeah? Do you have anything you want to add to that?
No.
And then finally, what you need to know is the rewards. So kind of speaking to our points earlier, if the state changes and you make an action, take an action, tell me whether or not that reward was good, was bad. So I think if you want to elaborate a little bit more on the cycle and the
Well-
observation space.
I mean, it's just really about the agent taking actions in some environments. And it's really about the actions, the step it takes. It's not, I mean, this is just a symptom of just looking at agents rather than straight X to Y mapping, where it's not necessarily about giving the answer, but taking the next step towards something. It's not trying to give the exact next answer.
Because if you had the answer, you wouldn't need reinforcement learning because you could just go from the problem to the solution.
Well, more like you're in an environment, you're like, let's say in a fighting game or something, the agent, the answer, like, what answer is there to I mean, there's options that are good and bad, but I mean, there's a goal to win the game, but like, there are many different options in many different situations that could work. For example, playing more defensively could mean blocking, it could mean dodging, it could mean parrying, like there's so many different things you could do, and it's not only just that, but it leads into a bunch of other things. And this is just how games are designed. And that, I guess, the fighting game analogy leads into like hierarchical reinforcement learning, which is like an entirely different field, but I really like it. So
Let's, I think we have, this is kind of goes to what you were saying earlier. So can you talk about the difference between the actual state and the observation?
okay, so the state space of here is all of Earth. The observation space, in my eyes, is all of this room.
Okay.
Like-
So,
I can observe this whole room,
Mhm.
but I don't know what's going on in Poly Canyon Village right now. So
but things outside the observation space, things outside the room can influence what's going on here.
yeah, just like or I mean, it could, maybe it's not. And then also the observation space from the chess is the same as the state space. It's just like the entire environment.
Okay. So in a way, observation is like a subset of the state space.
Yep.
And then what's the difference between discrete and continuous actions?
Well, discrete is like the amount of actions you can take is like, okay, in a game, it's just the buttons on your controller, whereas a continuous is like, or continuous can also be in game, where like, do I move, is the magnitude and direction that I move the controller stick this much or that much, like it's a continuous vector space on that, where like also self-driving is continuous, where like, it's not a discrete button press.
Mhm.
It's like you need to steer it into a magnitude and direction.
Can anybody think of more discrete and or continuous ideas? Let's start with discrete. What's a situation where you can only take specific finite actions? Like not a number, basically, not an infinite amount of numbers. Games are a really good example. Yeah, chess. Yeah, because you can't do an infinite number of things in chess. You have to pick your piece. Yeah. Jason,
It's all chess, checkers,
checkers. Yeah. What about continuous? What's more continuous?
Stock trading.
Stock trading?
Yeah.
You can keep trading stocks. Yeah, the number.
That's also one that just never ends.
That is true.
Like the Mario, it ends at the completed level, but that just never ends.
Yeah. Yeah, yeah, John.
Accelerator.
Accelerator in the car. Yeah, and this is also, the car is a really good example of also both actions kind of being possible in one, because a lot of the things like turning is a continuous action. How much do you turn? How much do you accelerate? But discrete actions also exist, right? If you're at a light, should you go or should you not go?
Or
Right.
if you're like gonna turn your blinkers on or not.
Yeah. Yeah.
I think also like the context of what you're driving can be different, and make it continuous or discrete.
Mhm.
Like if you're in like a blocky game where turning left consists of just turning 90 degrees, then that could be a discrete action. 'Cause
Yeah.
You have to turn 90 degrees left or right. But then like in real life, it's like you can either turn 20 degrees or like 40 degrees. So it's like you have to manage that more. There's a lot of different possibilities.
Yeah, depends on whether or not you're in real life. That's true. Onwards?
What?
Anything else you want to add?
No.
All right. So. Yeah, this kind of goes to
Yeah.
talk about what we were saying before.
The terminal state or not.
So episodic is kind of where you have like Mario Kart, where you have a starting point and ending point. Once you get there, you can say, okay, we've completed this action. Like we said earlier, stock trading just kind of goes on and you can keep making decisions, usually between 9 and 5 Eastern, but you kind of feed back into this cycle of go and go and go and keep trying to make money, right? Games are often episodic, I would say, unless it's like, I guess AlphaGo, no, AlphaGo doesn't go on forever. But, you know, with tic-tac-toe, you know when a game ends, there's 9 moves or less and you're done. Same with Wordle, or with chess, it's also episodic. I'm sure there are games out there like driving simulators that are continuous, but those are the two main differences. Yeah,
I guess it matters because since you don't have the goal in the no terminal state, it's a little bit harder actually. You have to be a little bit more creative with what you're setting, with the way you're training it. Like, because you can give like a big fat reward for completing the level. Like you know how employees they come back and they're like, oh, I got a fat check. And like you're not giving the model that check. So with the continuous thing, you have to like be really careful about the way you're balancing the rewards. Because it'll get very biased in terms of which actions it's going to take. You can't just have it prioritize the goal over all else. But even then, like that's not always something you might want to do.
kind of reminds me of, remember that article that came out when Bing Chat came out where it was like super horny? Like once you should read the New York Times. It got like, it was like declaring love to someone. So like once it gets off the rails, you know, and it kind of takes a step further wrong, and if that feeds into the reinforcement positivity, if that feeds it positively into the reinforcement algorithm, it'll just kind of keep veering off the rails. Like it'll easily be biased in one direction. You should look up that article, it's hilarious. Yeah,
So when you're training something for a continuous task, is part of that breaking it into episodic tasks, like constraining it at first, and then sort of letting it, and then transferring to continuous, or do you start it with the continuous task like right off the bat?
That's actually called curriculum learning. For example, if you wanted something to solve a maze, the approach I would take is first have no barriers, try to get it to like point A to point B in just like an enclosed situation. And then you want to start giving it past that like growing complexity, having it learn in a curriculum in order for it to be like deployed into a continuous state of learning.
so you kind of build it up essentially.
Yeah,
Although the end, when you have the complete maze, it still is like an episodic task, right? Because you still have a start and an end.
yeah, but I imagine it would go to having that start. There was a paper released on this, but like I mean it was kind of obvious, but like it was like they had Mario, and then it was like, oh, having it start, like no matter what you're doing, having it start with like already recorded player behavior is almost like a bias to start with, is always a better idea no matter what the situation is. And that made it so that it wasn't just starting off with just going in random directions everywhere. It started with something to work with.
By definition, you have to constrain it, because if you're trained never get to the evaluation point. You're basically you're not gonna be able to fix your problem. Right, so by definition, you have to, training itself is episodic, so you can't have something truly infinite in an episodic that.
Yeah, that makes sense. Yeah.
Usually what you do is that you have it have like a timeout or something, I believe. Like and then you can determine, okay, this throw this away, nothing happened. Or you can have it learn from it.
Yeah. All right, so onwards.
Yeah.
Any more comments? I don't want to cut people off. Okay, so this kind of comes to the practical applications of reinforcement learning. We know that the algorithm wants to interact with the environment. And do you want to talk a little bit about the frameworks available?
Okay, so basically there's really just two parts to this. There's the environment that you want the algorithm to interact with, and then you have some RL algorithm library that might use some deep learning framework under the hood. And the most popular one is Stable Baselines 3, and that uses PyTorch under the hood, I believe. My favorite, just for trivia's sake, is SKRL. It uses PyTorch, JAX and TensorFlow, I believe.
Okay, I'm actually gonna, sorry, I'm gonna come back to this in a second, because I realize this slide might be in the wrong place. The idea we have so far of an environment is this like place where an agent can interact with a situation, right? And it can be single agent or multi-agent. Maybe you have multiple players in a game playing each other. So to kind of motivate what we were just talking about, the frameworks that were available is this question: can we standardize environments in a way that we're speaking the same language, right? If we're all coding our own games and we're all coding how to, drive a car, maybe not drive a car is the greatest example because you can't code a real life, but this question of, if we're making games or language models or stuff like that, can we standardize the environment so that once we have that, we can experiment with different ways of doing the reinforcement learning? And of course, the answer is yes, because that is the topic of today's talk. So that's where Gymnasium comes in, and I'm sure there are competitors like Amir was sharing. It allows you to kind of create whatever environment you want, and it has specific ways that are standardized so that people can train on them, right? So kind of thinking back to what we said earlier about the Markov decision process, a more technical definition of kind of learning in an environment, the things you need are state, the action space, the rewards, and the probabilities. And so that's built into Gymnasium by default. So first off, we have the step method, which essentially is the action that you want to take. So the API is available for Gymnasium when you're training and when you're playing with the environment. You can call, and this is in Python, the step method, and you tell it what step you want to take. And then the environment, in response to that, will return the next state, and it returns the award along with some debug info and some other metadata. The next thing that's available is the reset method. So you can imagine if you're training a agent, you want to do a lot of iterations, a lot of episodes. And so you need to be able to kind of take that and reset the environment to a space where the agent can start again. And next you have the render, which is, again, just kind of for humans. We can see what's going on with the environment. And finally, you have close, which is, tell me how to stop, basically. So that is the core of the Gymnasium API. And then to bring us back to this, where that plugs in is the two parts that Amir was talking about. There's the environment and there's the actual learning. So Gymnasium is one way to bridge that gap between standardize the environments so that you can train and learn with different frameworks like stable baselines, stable diffusion.
Yeah, you can think of the environment as just this fishbowl that our little fish or agent is in, that is happening, and then like this is like we're over here, like a little dot up above, looking down at this environment. And you can even have like you can even parallelize it with your GPU and everything and have like multiple things, but that's a different topic. But like this, you get to see, observe from this environment that it's wrapped around, like, let's say Super Mario Bros. Like the actual game, by the way. Like this is not some knockoff. Like you can get the actual ROM and put it into an environment and then see the AI playing Mario. And then it extracts your like +1, whatever, like those scores and everything, as well as the actions it takes.
Let's take that a little bit. How can we take Mario and make it like, let's fit Mario into the 4 categories of the things that we need for the environment, right? So what's the state and what's the observation space?
Oh, observation space is like this, the screen usually. Okay, it depends. You can actually have it wherever you want, but I guess the research problems, they usually have all the pixels in the screen as the observation space, but you can just have it as like position on the screen as one thing in the vector, as well as like distance to a question block, distance to the nearest coin or whatever. Like you can have it as literally anything, but.
Question for the audience, what would be the action space? This should be mostly straightforward. What actions can an agent take when they're playing Mario.
Jump, move right.
Jump, move right, technically move back. You know, the things you can do on your controller, right? Those are the things that it can do. And what Amir was saying also should be, should make sense as well. The observation space is like what you can see when you're playing the game. Like if the agent is acting as you, what can you see? The pixels, what can you do? Whatever's on the controller.
A little asterisk on the action space, if you have like a fighting game, you know that like whole stuff that they do with like the. Like, okay, I'm doing it bad, but like, you know, the like little input stuff. Like, and then button or whatever, you can have this whole thing be an action.
What does that mean? What is that?
You can basically have a computer cheat. By having it so that it doesn't have to go through, like, in fighting games, you have to do some combination of inputs to do some certain move, right? Like, if you want, like, if you play Street Fighter, if you want Ryu to shoot a fireball, you have to like have a move back and press A or something. And
Or like drifting in Mario Kart, you have to like break and then turn. Into
yeah, like combinations of buttons. Or I don't know, in Wii Sports, one of them, you have to press A and B for something.
So you can have that be just one action.
Yeah, and I mean, it's kind of broken in fighting games because you don't have to have it learn the input.
All right. Does that kind of make sense so far? Any questions? I don't want to pause. I don't want to rush too much forward. Also, we're paying attention to Zoom chat. If you have questions, feel free to add. We have that up, but no pressure. Okay, so taking us forward. Again, these are the four main methods. And what's cool? So what's cool about what this GIF here is called the cart pull environment. So Gymnasium also has some built-in environments that you can use. So it has something called cart pull, which is essentially the game is you have a little cart and you try to move it left and right to keep a pole upright. So
Cart pull is like the hello world of RL, I think.
yeah, because it's very simple. You take two actions, you see whether or not it's falling over, that kind of thing. So this is an example of essentially how to use that carpool environment. The nice thing that we are going to utilize is how to make a custom environment. And don't worry if you cannot memorize what's on the screen right now. This is in the PowerPoint that we'll send out. But basically what you can do is you can imagine if you implement those four main methods of step, reset, close, and what was the other one? Step, reset, close. Render, thank you. If you implement those four, you can make your own. So this is an example that Amir pulled up of implementing Flappy Bird, right? So Flappy Bird is jump or don't jump, and reset is set the score to 0, put it back at the start, that kind of thing. So yeah, okay, those are all the slides I have. Is there anything else you want to add before we jump into some?
Well, I mean, I guess you can see how like all you're doing is that for Gymnasium, all you do is like you make your environment as a class that extends the Gymnasium environment, and then somewhere in your code you just register it using magical methods by Gymnasium, and then now all you need to do is just make you could just use it as a Gymnasium environment. In fact, step 3 is literally what you do even for the default stuff like cart pull, like it's just gymnasium.make cart pull 30 or something like that.
And that's making an instance of the environment.
So really the magic is behind step 1 and step 2. I guess that's why Gymnasium might be used a lot.
Yeah. So what I'm going to kind of prompt here is because so spoiler alert, the project that I'm hoping to launch in a couple of in the next couple weeks is a Wordle project. And so what I'm gonna suggest, since we have some time but not a ton today, let's work on brainstorming essentially how we can take Wordle and put it in this box of a Gymnasium environment. So we know that Wordle, we know that Wordle is essentially this box of a bunch of letters that you guess, and on and on and on. But question for the audience, is it important to have the actual pixels? If you're playing the Wordle game, what is most important if you are playing and you want to train an agent to play? What information would you need to have?
The goal is, I guess, are you trying to train an agent? Like, are you trying to be efficient or are you trying to do research?
Well, we're just trying to take Wordle and put it into a gymnasium environment.
Because you could do it in a variety of ways.
Yeah, so let's brainstorm. Let's ask the audience. What would you want to have in a Wordle environment like we're talking about? As an observation, like the state space. Any thoughts? Yeah. Letters in their respective positions. Yeah, so if you guess hello, you'd want to know which letters you have guessed and where they are. Awesome. Anything else that we need to know? Yeah,
Probably if the letters are in the correct position, or if the word contains the letters.
yeah. So if it's shaded as green
Green and yellow.
and yellow, sorry, not yellow. But yeah, so if not only the positions of the words that or the letters that you have guessed, whether or not they're correct, because that's how you assign a reward, right? What else is helpful? Yeah,
Like having the actual keyboard with all the letters.
having the actual keyboard.
For seamless.
Okay, so having a keyboard with all letters, so essentially, right, you have those kind of. I don't want to write out the whole QWERTY keyboard, but that way you know that you've used the L. And you know that you've used the H. That's helpful information. Yeah. Let's also think about the action space, and this is a trick question because I don't really have an answer. This is the point of the project, but what could be the action space of Wordle?
Oh, yeah, how does Wordle work again? It's like the second time I've heard of it in my life.
Okay, fair enough point. Let's do a review in case anyone hasn't heard of Wordle. So it is a 5x6 board of letters, and the idea is there is a word that you're trying to guess, and you don't know what that is, but you can guess other words, and it will tell you if, for example, hello, it will tell you if H is in the right place in the word and you guess hello, it will shade H green. And then if O is not in the word, it will shade O gray. And then if you have an E in the word, but it's not in the right place, it's somewhere else, it will shade it yellow. So with that information, you're trying to guess the word that it has. Does that make sense?
Yeah.
And you get 6 tries, I believe, not 5. Yeah.
Words.
Yeah.
Can you only input words or can you input any string of 5 characters? This is the essential question. I tried to do a little bit of playing with this a couple years ago, and that was the main question, right? So when a human plays it, what can we do? We can't actually do either of those. What step can we take individually? Let's do with this. We can only, yeah,
We can only type in one of the letters that set.
yes, we can only type in, and then once we get to 5, we can either hit enter, right? So kind of coming back to what Amir was saying about the combo, like if you have that like drift that you want to do in Mario Kart or a special move in a fighting game, we can kind of cheat a little bit and we can either have the computer guess a whole word or guess individual letters or something else, right? So this is kind of an open question. Can we think a little bit about what would be pros and cons of having it be any string versus only specific words and maybe versus specific letters? What would be kind of a benefit of having it be letters?
I mean, that's what the game is about.
Yeah,
Or
more
it's-
realistic.
Yeah, if you had the words, it only knew words. It's not. It's guessing words. So like, it wouldn't have that feedback of, oh, this is in a word, this is not.
Yeah,
I mean, actually it could, because if you algorithmically restrict it afterwards to, it's guessing space to be X or Y,
Yeah.
but still it's not gonna have the, actually it depends, but like, it's not gonna have that association of letters to words.
More realistic and has a better association of letters to words to guess letters. Yes.
Though I suppose there are ways around it.
Yeah, another thing I was thinking is if you have 26 letters and enter, that's a smaller action space compared to if you're doing any random string and or another thing to consider is Wordle only allows certain words to be guessed. So, and there are actually about 11,000 or 10,000. So if you want to have that be your space, you have 10,000 choices, and maybe you would need a lot more time and training to have an agent learn which of those 10,000 to choose, right? Any upsides or downsides to either of those? Because I have a couple more downsides to talk about, but I want to see if anyone has thoughts first. Yeah, James or
Julian.
Julian?
Go ahead, Matt. Oh, I was wondering about, did you say it was easier for it to guess words or like strings?
So it is not necessarily easier in any capacity. The question is if it can guess any number of strings, or if it can guess any random string, that space, the action space would be like 26 factorial, or 26 to the power of 5.
I guess to better put this into context,
Yeah,
imagine it could guess like the number 0 is mapped to the 3D model of Leo. The number 1 is mapped to I don't know, any one of these names. Like you're just mapping it by number, which is why it's not easier or harder to guess certain things. So you're just, it's like 0 would correspond to the letter A. Or 0 could correspond to I don't know, animal.
the guess itself isn't harder. It makes the problem space bigger, which introduces different problems. Or excuse me, the action space bigger. Yeah. That can help.
Yeah.
Julian, what did you want to say?
I was gonna say, if you don't restrict it to words. It might like take longer to get there, but you might end up with some weird strings that are like probability based.
Yeah,
And you could end up having it be like much better than you could ever do with real words.
yeah.
I actually have a funny story on that, but that could be saved for later.
All right, why don't we can chat after the presentation. That's a really good point, because like, you know, the idea that machine learning can come up with answers that we never thought of possible is exactly that. It would take forever to train, right? Because you can have it do whatever. Yeah, those are the main thoughts that I had. The kind of keeping in line with that, if you have any random string be able to be guessed, it kind of has to either relearn English to see what guesses are valid, or you have to train it a heck of a lot more, right?
There is another option.
There's
You
another
could-
option,
You could have it be doing parts of words. This is what ChatGPT does, by the way.
tokens.
Yeah, well, I mean, like everything that we discussed were about tokens, but like, you could have it have like basically just parts of words, like ing is like the end of the word.
Suffixes and prefixes
Yeah.
and things like that.
There's a really nice website. It's I believe it's ticktokenizer.vercel.app. And it visualizes all that.
Cool. Okay, so we have our kind of observation space and action space brainstormed. We don't have action space answered. But let's think about the probabilities, and this is also an area that I myself am not quite clear on. So I'm gonna kind of propose that the probabilities would be essentially when you guess 5 letters, you move on to the next one. Like guessing the 5th letter is 100% chance of going to the next one. I'm actually gonna read a little bit more into that and follow up in future weeks, unless anyone wants to add something specifically, because I'm not too clear on the probabilities myself. So what I'll skip to, unless anyone wants to object and tell me right now, Leah, this is how this works. But what I'm gonna skip to is the rewards. So this kind of goes to what you're saying earlier, the mapping of the letters to the information that you have. What information can tell us about the reward that we should give to an agent for what actions it takes? what information do we have and what should we reward as good and bad? What's a good guess? What's the best guess? The actual word, yeah. If you like on the number one try, guess the actual word, that's like 100 points. You get bananas and chocolate, right? What's an above average guess? Like what is very good? Yeah, John.
You can make your reward directly proportional to the number of words you eliminate out of the problem space.
The number of words you eliminate out of the problem space. So if you guess a word and it takes down 90% of the other words because they have. If you guess a word that has H at the beginning and it eliminates all of the words that don't have an H in the beginning, you've just gotten a lot closer to your goal. So that was a good guess. Right? So that is one approach to take because every time you narrow down what you're trying to do, you make progress. Good job.
What if you had a multi-agent system where one of them was guessing straight up words proportional to the amount of words it eliminates out of the problem space?
Yeah.
And then the second one comes in, it's like relay race and does the tokens of the parts of the words. Well, I mean, if the first one decides that the second one should go, or it could decide that the third one should go, which is also the second one could decide whether the third one should go afterwards, which is doing by character.
So each row might have a different agent
No.
guessing.
No, all three of them, they all collaborate on one word.
Interesting.
So they're gonna sample.
Yeah,
Are they
like,
all working at once?
if it was like, this is the word one, it might decide, depending on whether it was close, like if it decided like, if it guessed hell and like there was only one left or something, it could go to the character one. Or if it's not like that, it could go to the token one, or the token one afterwards could go to the character one if it wanted to, something like that. And then you wouldn't use gym, you would use petting zoo.
Interesting. That's a way you can have all three collaborate to guess a word. I didn't know that. Yeah. Do we have any other approaches to rewarding? One's narrowing down the problem space. Any other thoughts?
I feel like the naive one would be just based on how many green, how many yellows you get
Yeah,
from the guess.
that's the approach I took a couple years ago. Was if you guess 2 green letters, that's like 10 points. If you guess 2 yellow letters, that's 8 points. 4 points per yellow, 5 points per green. And actually, in that case, good thing to keep in mind is that gray letters are actually still good because it tells you some information about what's not in the word, right? So just keep in mind that gray letters are not 0 points because you have made progress, kind of like John was saying, you've narrowed down the problem space if you guess gray letters. But yeah, that's another approach I took.
Why don't you just try all of them, all these approaches?
So that's what I'm hoping to do is we have a good group of folks who are here today. So I'm gonna kind of pack all of this up into some instructions. Since we're approaching on 2 o'clock, this is perfect timing. But so upcoming, we have I'm gonna do a little bit more research on Gymnasium. That's the environment library. You should feel free to as well. And then coming back at our next project meeting, what I'm hoping to do is propose this and maybe get some groups together. One group can try, if you really want to work advanced with a mirror, you can try 3 different ways. There are 3 different agents. One group can try having the problem space, one group can try having the action space be like all possible strings. One group can try having the action space be only these 26 letters, one at a time, things like that. Because then maybe we can kind of try things and see who ends up with a good bot. Kind of propose that in the future weeks. Yeah. So that's a nice little place to kind of tie us up and bring us to the end. Is there anything else you would like to add, Amir?
Advice is like, if you're not sure, you just always give it a go.
Yeah,
Like you're not just jumping into a pool of lava. Like it's never gonna hurt.
never gonna hurt. So if you would like to, over the next 2 weeks, we have something scheduled for next week, so we're not gonna be able to work on Wordle, but in the coming weeks, if you would like to, feel free to try to make Wordle in Python. You know, all you have to do is basically you have a word every time you guess, assign green, yellow, gray. If you want to keep in mind gymnasium, right? What's a step? What would be that step function where you take an action? That's a guess, right? That's a Wordle guess. What's reset? Okay, clear off the board, get a new word, get that going. Feel free to dip your toes in the water. If not, no worries. I can put one together and have one for us in a couple weeks, and then we can kickstart reinforcement learning from there. But yeah, this is step one to Wordle AI coming soon. Yeah?
Yep.
Awesome. I guess that will wrap it up. Thank you for your attention.